Okay, it's my great pleasure to introduce to you Laura Waller. She is an associate professor at the University of California at Berkeley. She did her PhD at MIT and was postdoc at Princeton. And she's going to talk about computational microscopy for neural activity tracking. So Laura, it's yours now.
Thanks. All right, so I want to talk about general computational microscopy first, but also getting into like one application that we're doing, which is in neural activity tracking. So I won't actually get there until towards the end. But sort of the general idea of computational microscopy is the general idea of computational imaging, in which you want to design your imaging system, hardware and software together. And you get all kinds of like efficiencies and synergies by treating this sort of like system as one big design problem rather than separate hardware and software things. So whatever is best done by the optics, you do with the optics. Whatever is best done by the computation, you do in computation. So I sort of take this into two parts, where you sort of have some sort of imaging system you're trying to design, and you have an object X that you're trying to recover by taking some measurements Y, and you get to design this A, which is basically your microscope's system function. It can be linear or nonlinear, whatever, but you get to design it within, physical constraints and cost and complexity considerations. So this is like the imaging systems design part of it, and it's more like a black art, right? You have to think about what's the best way to transfer information from X into those measurements Y without having a system that's costs $1 billion or is physically impossible. And then once you have these measurements and you want to solve for X, then you need to solve the inverse problem. So this is the algorithm piece of it. And this is often much more straightforward once you've designed the system, but the whole key of computational imaging is that these things should feed on each other, and that knowing what kinds of inverse problems you can solve and solve more easily allows you to design systems that are more efficient. And so I hope that I can give you a couple of examples. But in all the work that I do in computational imaging, the hard part is really this integration. This is like a systems engineering problem. And you have sort of your hardware toolbox, which is all of the optical elements you might put in, the sensors that you have, and then your computational toolbox, which is like, we only have a certain amount of memory. We have a computer with 1 terabyte of memory, but not everybody has that of RAM. And sort of like, how can you parallelize things? So you need to think about that in the design process. And I want to show a couple examples of how we can really push the limits of imaging with existing physics and commodity hardware. So without using any fancy newly discovered physics or any custom built hardware, we can sort of put together off-the-shelf things and do imaging tasks that otherwise would have been really expensive or really difficult. Okay, so I'll give an example. And this is sort of like, this is a real example that I'm going to talk about a little bit, but this sort of fits with the computational imaging pipeline. So here's like a classic question in computational imaging. Can I take a camera and remove its lens and then do lensless imaging? So my hardware design in this case is a sensor, and I've just got some light hitting a sensor from my scene, and I take a picture. Of course, it looks like a big blob. And the question is, can I take this picture and recover the scene from it? So there's light coming from the scene, and so why shouldn't I be able to backtrack where that light came from and get to what the scene looks like? And if you ask the question, can I recover the scene from this image? The answer is basically no, because you don't have any way of solving the inverse problem. So what we do is we put this diffuser in. So the diffuser is really just like a bumpy piece of glass. It's literally like the stuff that you put on your windows for privacy, so like privacy glass sticker stuff. So if I put this privacy glass sticker stuff in front of my sensor, then it sort of just like messes with the angles of the light, and then it propagates a small distance. And what you get is a picture that also looks like garbage, but now it's structured garbage. And so if we can calibrate this system, we actually can solve an inverse problem and get back a picture of our object from this single image and do this sort of like lensless imaging. So I think you saw a talk from the FlatCam guys, Ashok. This is really similar, except this is a phase mask, and we didn't do any fancy design. We just literally taped a piece of this diffuser sticker onto our sensor. So we call this DiffuserCam. This is what it looks like. You can build it on a Raspberry Pi, so it's dirt cheap. And there's really no calibration. You just stick this thing on, like it's literally scotch taped on there. And you can start taking pictures. So our model is also different than some of the other lensless camera designs, which I'll go through. But the main idea is that this is a computational camera in the sense that it is not a one-to-one imaging system. So the measurements you take in Y are not directly related to the object you would like to image in X, which is what you traditionally do. So normally you try to design your cameras such that the imaging system, like matrix describing what the imaging system function does to your scene is one-to-one, that it's identity matrix. You buy really fancy lenses to try to get this as much of a diagonal as possible by avoiding aberrations and such. Also that you don't have to do any computation, so that what you measure is your final result. Whereas a computational camera is more like a linear combination of different things at every measurement. So every pixel in Y now measures a linear combination of information about different pixels in that scene that I would like to image, which is X, right? And as long as A is invertible, I can inverse this, I can solve this inverse problem to figure out what X was, right? And so I want to argue that computational cameras, because they have this sort of multiplex measurement in which every pixel measures linear combinations of information from different pixels in the scene, this can be better. And this is what allows you to do compressed sensing. But sometimes, like, if this A matrix is invertible, you can do a lot more with this kind of system because it's multiplexed. But for now, let's just say, like, we're trying to do it in order to make things lensless, which you have to have this multiplexing, because if you don't have a focusing element, then every point on the scene will map to lots of pixels in your sensor. So for this DiffuserCam, our measurement looks something like this. Our object looks like this. And this A matrix is essentially the image that I would get. Each column of the A matrix is the image that I would get on the sensor for a point source, an incoherent point source at a particular position along this X matrix. So X is just a raster scanned scene that I'm trying to image. And if you take a particular point in the image, there's a column of this A matrix that describes what's the sensor measurement I would get if I turned on a point source at that particular point in the image. And then my measurement is essentially just a linear sum of all of those things. And if they're all unique, then I can decompose my measurement into these different sort of, we call point spread functions. So what you see the point spread functions look like, they look like caustics because our camera is a diffuser propagated by a particular distance. It's not that particular, but it's approximately the caustic distance of this diffuser. So you see these caustic patterns. And we need them to be unique for each different point in the scene. So what I'm going to do now is to show a video. But in this video, I'm taking I just turned on the flashlight of my iPhone, and I'm moving it or waving it around. And what you see is this like point spread function caustic pattern is shifting around, and it's shifting around in exact proportion to where my point source is in the scene. And so what we have is that because this diffuser is a thin phase mask in the caustic regime, which is why we designed it that way, it creates this point spread function that simply shifts with lateral position of the scene. And this is wonderful because if I were to try to completely characterize this, if I had no idea what this A matrix was, I would have to go measure it. So I'd have to turn on every point in the object scene and measure a 2D image for every point. So if I have 5 million pixels in my scene and 5 million pixels in my measurement, this is going to be 5 million squared, and I have to go measure that whole thing perfectly, and then nobody's allowed to sneeze before I take any measurements with it. So instead, we're going to use this model wherein it's the same point spread function, but it shifts, which means I only need to calibrate this thing by taking a single point spread function measurement here. And I know it's simply going to shift, and it's going to be the linear sum of a bunch of shifts. That's exactly what a convolution is. So what I say is that my measurement is the point spread function convolved with the scene and the object. So it's a little bit more complicated than that, because as the point spread shifts off the edge of the sensor, we need to account for that cropping, which we do. You can simply put it in, so it makes it a little bit, not quite a convolution, but pretty much the idea is that it's a convolution. We also sometimes add some regularizers that are nonlinear, but I won't really talk about that right now. Okay, so then I give you this raw sensor image, and you can tell me what it looks like. It's a picture of me. So you can see that we're still working out some artifacts, but now we can do video rate stuff. And it looks like the raw sensor data is pretty like a big white blob, but if you zoom in on it, there's actually quite a lot of detail, which is why it's still a not too ill-posed inverse problem here. And I can give you a lot of arguments why this is actually a very good point spread function to use, because it's distributed, which means you can do all kinds of stuff with the multiplexing, but it also has really sharp edges. So the spatial frequencies that exist in those caustic patterns are diffraction limited spatial frequencies. Okay, so then we want to do 3D. And so we just take our point source and we move it in depth away from the sensor. And this is like relative distances are actually relatively small. This is, from a millimeter to a few centimeters away, maybe further than that. And what you see is the point spread function isn't changing very much other than scaling. So it scales with depth and it shifts with lateral motion, right? And this is the model that we're going to use. We call this the convolution model. So basically our 3D forward model is now that the part of the scene that is at one particular depth is a 2D convolution with this point spread function. And the part of the scene that's at different depths is convolved with the same point spread function, but it's scaled differently at the different depths, right? So this is a really easy model to write. You only need one point spread function measurement to calibrate the whole thing. In practice, we actually take a couple because it is changing a little bit in the axial dimension, and it just works better if you take a couple through focus images for the calibration. But then we can just decompose this single image measurement into these 3D things. Okay, so the problem with it is it's extremely ill-posed, right? 5 megapixel measurement, I'm trying to solve for 5 megapixels at each slice of these different depth slices, and we sometimes have 100 depth slices. So if you look at this y equals ax problem, now my x is raster scanned image, but at each depth. So this will be like, the first chunk is Z1, Z2, Z3, Z4. And so now that's like 100 million things I'm trying to solve for from only 1 million measurements in Y if I had a megapixel size sensor. So this is underdetermined by a factor of 100. And can we solve it? Well, sometimes. And so the sometimes is when you can use compressed sensing. So if your object is sparse, which objects in 3D tend to very much be sparse, and I'll show you later our neural activities application is always sparse, then you can use this ideas of compressed sensing. So compressed sensing is all about solving underdetermined problems exactly if you can make a prior on the object that it is sparse in some basis set. And this works great for, you need 3 things for compressed sensing. You need incoherent measurements, which basically incoherent means some sort of multiplexing. And ours is it is an incoherent measurement, but it's not very incoherent. So it's not the perfect situation for compressed sensing. You need sparsity in your object, and you need an L1 regularizer in your reconstruction problem. So we have all of these things. So we can take one of our raw images and simply delete 80% of the lines and still reconstruct a pretty good image. That's a good sign, but nobody would ever do that, right? Like, why would you throw away pixels that you measured? That's not super useful, but in 3D, it becomes extremely useful to do this sort of like data compression in the capture stage by using priors. So here's the raw image that we take, and our object now is this US Air Force target, but it's tilted in the 3rd dimension. So it's like sitting 45 degrees diagonal to the camera, and this is just like a rendering of the 3D reconstruction. So we actually do get the optical resolution out to approximately what we would expect, and across a pretty big volume, although this object doesn't occupy much of the volume. So actually our reconstructions end up having about 100 million voxels in them. You can clearly see we're not using all of them here, but we could do that because it's in this weird conical shaped field of view. But we're reconstructing more voxels than we measured pixels in the first place because we can do this sort of like sparsity enforcement. Here's another object. This is like just a little leaf. So you can see a picture of it here. And there's a single raw image that reconstructs this 3D stuff. Okay, so I wanted to talk about that because I'm going to get to that a little bit later. We're going to use it for neural activity tracking, but we haven't totally gotten there yet. So I want to go to something a little bit different but related. And the idea is that we're doing this 3D imaging from 2D measurements, but we came at all of this in terms of phase space or light field imaging. And I suspect a lot of people there actually know a lot about light field imaging, but maybe don't know much about the Wigner function or wave optics versions of it. So phase space is this general term that means any space angle functions. And within phase space, you can break it down into light fields are basically the space angle functions for ray optics. So they're assuming incoherent ray optics only. Everything's geometrical optics. They can't account for any wave optics. People have tried to add wave optics things to the light fields, but there's already lots of constructs or functions that you can use to describe space angle functions if you have wave optical models. And the Wigner function is the most popular, but there's lots of different choices here. Basically, spatial coherence functions are exactly related to these phase space functions. So it's like coherence measurements, spatial coherence measurements. So Wigner function is similar to light field in that it has two spatial dimensions, x, y, and two angle dimensions. So ux, uy are spatial frequencies, but when you're talking about a wave field, the spatial frequency is directly related to the angle of propagation. So you can think of ux and ui as theta x, theta y being exactly the same thing. They're directly related. They're directly proportional for monochromatic light. And I'm going to use them interchangeably. So everything that I'm going to show is actually in the wave optics phase space regime, which we're using Wigner functions. But Wigner functions are basically exactly the light field analogy, but for wave optics. So I'm going to completely switch back and forth, and I might even call them light fields, even though we're using Wigner functions, because some people get scared when I call them Wigner functions. But everything's the same. Propagation is a shear, a point source makes a line. The difference is that Wigner functions capture interference and phase effects. So you can see like diffraction ringing effects here, which you would never see in a light field plot. So they additionally capture stuff, but they, in the limit, they become the light field when your object is incoherent and ray optics applies. Okay, so just like light fields, your Wigner function has space and then angle. So this is just a slice. You actually have a four-dimensional thing with x, theta x, and y, theta y, right? And what you would normally measure with a traditional camera or traditional pixel is intensity, which is the sum of all the energy across all possible angles. So you take a projection of this light field space across all angles. So you integrate it across all angles, all of the energy that hits a point in x, and that's your intensity at that position in x. If you integrate across the x dimension, then what you get is the angular spectrum. So this is the intensity of light you would see if you did a 2F system to make a Fourier transform of your light and then took a picture. Okay, so normally we measure these projections of this four-dimensional phase space, and we want to measure the whole thing because this higher dimensional stuff is going to give you more information, right? So I like to think of it in terms of coherence functions. So for a coherent, spatially coherent system, you can basically think of it as some wave field in which at every point in the 2D plane that you care about, there's an amplitude and a phase. So this wave field can be fully described by some 2D complex field with a single amplitude and phase at every position. Whereas a partially coherent beam, at every position on the 2D beam, you actually have a statistical distribution of phases and amplitudes, which results in a 2D statistical distribution of directions of propagation or angles. And so you end up with this four-dimensional function. And therein, partial coherence is uniquely tied to phase space functions. And basically, these four-dimensional phase space functions measure four-dimensional spatial coherence properties when you use Wigner functions. But my point in this slide here is really that if you have a coherent system, you only have one amplitude and phase at every point. So the slope of the phase is directly tied to the slope of the phase is the slope of this wavefront, which is always perpendicular to the ray direction. So the direction of propagation is always directly tied to the slope of the phase. And so the slope of the phase will uniquely dictate what sort of like a wavefront shape you have here, what angle the light is traveling at every position. But fundamentally, you can only have one angle of propagation at every position because you only have one phase at every position. And for partially coherent light, that's not true. You can have this whole distribution. So, so coherent stuff in four-dimensional space is really just a two-dimensional manifold within the four-dimensional space. It's not filling in the whole space at all. But partially coherent light can, and totally incoherent light at a distance is partially coherent. And so you can sort of like use this four-dimensional space more. It means you're using the degrees of freedom more. So we're pretty much only going to deal with partially coherent stuff. And by that I mean basically incoherent emitters spaced in 3D, because they incur more coherence as they propagate. So so you can think of it as an incoherent scene, but the light at the camera will be partially coherent. Okay, so I want to talk about scattering, and you need this if you want to do neural activity tracking. And this is like one of the classic problems of optical imaging is trying to invert scattering, trying to image things through scattering material. And of course, everybody knows this problem, right? You would like your light to go straight through the object, and some of it does, very little of it does, but a lot of it gets scattered. It bounces off these little scatters in the object and sort of like randomly changes direction and then comes out at some other random direction, right? And most scattering imaging techniques of past have attempted to just get rid of all of the scattered light and only collect this ballistic light, so the light that happened to not scatter, which is only a tiny fraction of it. They try to like filter out all the scattered light and keep only the light that didn't scatter so they can get a nice clean image as if it hadn't scattered, right? So we don't want to do that because there's far too little of the light that actually doesn't scatter. We would rather sort of try to measure something that allows us to invert the scattering computationally. So model the scattering and use that light to help reconstruct the image. And if you've got a very highly scattering material, then you've got exponentially increasing degrees of freedom with the number of layers and the amount of scattering. And so we do other stuff in other areas, like looking through cells and stuff, where there's not too much scattering, and we try to actually reconstruct the whole scatter function so that you can completely undo the light, how the light went through the scattering material. But when you've got a lot of scattering, it's kind of hopeless. You're just never going to measure enough information to be able to uniquely invert this. So what you need is statistical models. And I want to sort of point out that if you're going to use a statistical model about how things scatter, then for example, you could just say like, okay, the light should have just gone straight through here, but it sort of some of it scattered all over the place, and you end up with sort of like a big blob of light instead of just a point. And so so you could just try to like look for a blob and then like deconvolve it into a point. And everyone knows that doesn't work very well, right? It just, if things get convolved with big Gaussian blobs, it's very hard to undo, right? So I want to make the point that measurements in 4D are useful for doing this kind of thing better. And the idea is that scattering mixes space and angles. So the light is, as soon as it hits the scattering material, it scatters out to different angles, but then it's propagating, and then that scatters out to different angles. And so light comes out here at a distribution of positions and angles relative to what it should have come out at. And so the idea is that scattering is changing the angle of the light and over space, which is changing your positions. And so measuring space and angle information, like having light field or phase-based measurements, should give you some hope for trying to invert it better than just a 2D intensity image where you have no idea what angle the light came in at, right? So this is the example situation that got me started on all of this. And this was an experiment that I did as a postdoc at Princeton. I was not trying to do anything through scattering. I was trying to do something completely different with nonlinear imaging, but I had this like 3 bars resolution target, which was my image, and I put it behind a rotating diffuser. So I just had a rotating diffuser in front of it. And so of course the image gets completely blurred out because it's going through this highly scattering, dynamically scattering thing. So then I was doing phase-based measurements, and I took a phase-based, so that the phase-based measurement would be a 4-dimensional thing. So I'm just gonna show you a 2D slice along this red line of x, theta x. And what you see in this phase-based slice here is that the 3 bars are clearly still visible in the phase space. They're tilted because this thing is off focus, and they are blurred out, right? They're just not as blurred out as this 2D image. So cross-cut line of this just looks flat. You can't recover these bars at all. And it makes sense, right? If you think about the projection of this phase-based plot would be your intensity image, and it will be just flat. You won't be able to resolve these 3 things, but in the phase space, you can. And so it's like trying to think about like, oh, this is cool. There's still some information there in this phase space that's not there in the 2D image. And how can I like use that to image stuff through scattering, right? So one of the first thoughts was to use the ballistic light, and I think I've seen a paper doing this in photography, where you basically like just say like, let's only take the ballistic light. So the ballistic light was the light that only went at theta equals 0, so it didn't scatter, so it didn't change angle. It was, so we illuminated this thing with light on axis, and it kept going on axis, and you will definitely get like the 3 bars distinguished in this ballistic light, right? So that's great. This is the like filter out all the unscattered light. This is a great way to filter out unscattered light, right? But this was, taking this is exactly equivalent to simply taking my microscope and stopping down the aperture, making it very, very small. And the problem in microscopy is that when you stop down your aperture, so you only allow a tiny range of angles through the system, not only do you lose a lot of light because you're just blocking all of this light, but more importantly, you're killing your resolution, because resolution in microscopy is all about numerical aperture, which is the range of angles. And so if you kill the range of angles, you're killing your resolution. And that's the only reason you do microscopy in the first place. So it simply is not compatible with microscopy. Maybe in some photography applications that are very bright, this will work. But so we didn't want to do that. So we want to actually use this whole phase space function to recover the object through the scattering media. So here's our model. We're going to go to point sources. And for all this neural activity tracking stuff, I'm going to treat my neurons as if they're just point sources that light up. So if I have a single point source, and say I care about the light field at this particular plane z equals 0, and I've got this point source that's at some different depth. So this is axial dimension here, and this is lateral. If I plot the x, so this is x, theta x for this point source, it's off focus, and so it's giving off light in all possible directions. But as you go up along x, the angles are getting larger and larger, so it's actually this tilted line in the phase space, right? So a single point source off focus is a tilted line, and this is really beautiful because the x crossing tells you where it's at theta equals 0, so the x crossing tells you its lateral position, and the slope tells you its depth. So if so this is a depth that's on greater than 0 side of focus. If I put a point source on focus, it will just be a vertical line. So its slope is just this vertical line. If I put one on the other side of focus, then it tilts in the other direction. And so the amount of tilt tells you its depth. Anyone who knows light field already knows this. And the idea is that we already knew this, right? You can take a phase space or light field measurement and fit it to a bunch of lines, which are really like 2D hyperplanes in the 4D space, and you can find point sources in 3D. Great. And you'd never find them from this intensity measurement, even now without scattering, because you don't know if it's in front or behind focus when you see this big blob here, right? Okay, so that's great. But I'm supposed to be talking about scattering. So what happens if I put these 3 point sources in a scattering medium? Well, it does something like this. So this is on and off with the scattering. So when it's going through the scattering media, what do you see? So we're currently like focused on this middle one. So the middle one is this one, is a vertical line, but it's a little blurred out. So this one is the one that's like going through the least amount of scattering, and it's the least blurred line. And this one back here is going through the most scattering. So it is both tilted in this direction a lot, and it's blurred out a lot. So, and in fact, if you model, so we have this like fancy multiple scattering model with Wigner functions that fully accounts for wave optics. And what you end up with is basically the lines blur into 2D Gaussian blobs of particular width, depending on the scattering functions. And the cool part is that now depth of the object is not just a different amounts of tilt of these lines, but also how much the lines are blurred out in this 4-dimensional phase space. And so that's a very strong physical model that we can use as a prior in an inverse algorithm. So now we don't want to go and fit this to lines, because obviously we would never recover this sort of like big blob in the background, but we want to fit it to blobs that of a particular tilt angle. And this is all happening in 4D. I'm only showing the 2D slice, right? So you can just set this up as a y equals ax problem. You take these measurements, you're trying to solve for the 3D positions of the point sources, however many there are. Basically, you try to solve for the intensity in all the 3D points, given that each point would create a blob in 4D phase space of a particular tilt angle and like spread. So this is great forward model. when you use Wigner functions, it works for both wave and ray optics. It doesn't care about coherence or incoherence. It doesn't care about dynamic or static scattering. It works equally well for both. And it can capture multiple scattering effects in a statistical way, which is the best you can hope to do, I think, here. So you just solve an optimization problem to get this. We're putting a sparsity constraint, which adds an even stronger prior, that it's a bunch of point sources in 3D that are sparse. So forward model plus sparsity are very strong priors. This is going to allow you to solve this problem in places where it's very highly scattering that you wouldn't be able to do for sure in 2D. Having stuff in 4D, it's highly compressible in 4D, which is good because you're using this, you're trying to recover 3D from a 4D measurement, but that helps you to sort of like mitigate the scattering effects. It gives you robustness to scattering. It's not just wasteful extra dimension. And we're including multiple scattering in our model, which is very useful. So how we solve it is basic optimization, nonlinear because we've got the sparsity prior. So you take your old estimate and then you update it. So your update will be some sort of step size and then search direction. And the search direction is the important part. You can just do gradient descent. We typically always do these second order methods because we've found that they perform a lot better for this problem. Not exactly sure why. They're not just faster, they actually get to better answers, I think because it's a non-convex problem. Here's my video of why second order methods are better, because they're more exact and so they don't need to have a billion iterations to get to the answer. But actually they sometimes get to the answers that the gradient descent cannot get. So LBFGS is really easy to use out of the box. If we can write the Newton's method or sort of a quasi-Newton method, we'll do that if it's not too crazy to actually go through the Hessian or some approximation of the Hessian. But I think most of the results I'm going to show are from LBFGS, although I know Herbert changes his mind all the time on which algorithm he's using. So we've used a lot of the proximal algorithms as well. And I can't promise everything is the same algorithm used here. Okay, so here's some simulations. And my point here is like, is this going to work? Yes and no. So it works much better than trying to just decompose a 2D image into intensity blobs because you've got higher dimensions, right? And this like 4D provides robustness, but it does break down eventually, right? You're still blurring in this 4-dimensional space. So eventually these things become indistinguishable in the 4-dimensional space. And it's all dependent on sparsity, right? So the more sparsity you have, so less density is good, right? The more point sources you have, the more blurred everything gets together, the harder it is to solve this problem. So density matters, so sparse is good. And then more scattering also blurs more. We can model it, but that doesn't mean it makes it easy, just as easy to invert. This is a harder problem to invert than this one. And so less scattering is good, less density is good. But actually this plots that I'm showing you, these are all cases in which we successfully recovered the ground truth object in simulation. So my point is that like this looks really bad. This looks impossible to solve for all of these particles, point sources here, but you can do it because I'm only showing you a 2D slice of 4-dimensional, and the algorithm has really strong priors going in here. Yeah, so that's the idea. And I've been talking about all of this as if we just have these phase-based measurements, but measuring 4-dimensional things is obviously not that trivial. So how do you measure this phase space or light field stuff in order to get this data so that you can solve these inverse problems? And so the traditional way of doing it is with light field sensors, with putting a lenslet array in front of a sensor. I think probably most of you have seen this before. When you get light coming in at different angles, it hits different parts of the sensor. This is basically the identity matrix version of measuring your 4-dimensional lights field. So you take your 2-dimensional sensor and you multiplex angles and spatial measurements into this 2D thing. But that means that you end up with, you know, if I have 10 to the 7 pixels, then I'm going to end up with only a few dozen angle measurements at each position and only a few hundred positions in each direction because I need to split my 2D sensor up into a 4-dimensional measurement. So if you think about this in the light field space, basically each pixel measures the integrated information across one of these boxes here. And I can choose the lenslets to squash the boxes or stretch them in either direction, but I fundamentally can't add more boxes because that's the number of pixels, right? Okay, so getting back to DiffuserCam, the actual original reason why we built it was as an alternative to lenslet array light field sensors for microscopy. And the idea was that when you put this diffuser, it's kind of like a bunch of small lenses, but they're all random. They are all randomly placed, have random different focal lengths, and they're all overlapping each other. And that results in a multiplexed light field measurement in which basically each pixel on your sensor measures a linear combination of different information from the light field space, which maps to like weird integrated swaths of this light field space. But you can map them all out. It's a linear inverse problem, and you can solve it. And so this is essentially just the multiplexed version of the lenslet array light field measurement. But the multiplex version is really useful for a couple of reasons. So one is that it's flexible. So if you have a lenslet array, you have to choose those box sizes when you're constructing the camera. And then when you want to, change the NA of your microscope or like change how you measure things, then you cannot, right? You have to keep the you want to keep the apertures of your lenslets matched to the aperture of your main lens in the microscope. So that's NA matching or like aperture matching. And so it's not flexible for changing different apertures, which you like to do very often in a microscope. This multiplex version doesn't care. It doesn't have a particular focal plane that it cares more about than the others as much. But I think the cool thing about it is that you can start doing compressed sensing because you have these multiplex measurements. And basically the sparsity priorities I talked about before are compressed sensing. So we need to do that. Okay, here's just an example. This is from last year, a while ago. So we were reconstructing, this is linear problems, reconstructing the light field from this single measurement taken through a diffuser. This was like replace the lenslet array with a diffuser. The other big reason to do it is it's dirt cheap. The lenslet arrays are kind of expensive, and to get high quality ones is very difficult. So here's the measurement. You can see that it looks like a picture taken through a diffuser. This is 2 playing cards, and we can digitally refocus. So just using a shift and add algorithm once you have the light field. So we still had some artifacts here. We're getting better and better at dealing with this DiffuserCam's calibration and artifacts issues. This is older than the DiffuserCam stuff I showed earlier. Okay, so we can do this. So now if we can measure this light field, we can fit it to this scattering model and try to find point sources, which are the neurons that we're looking for in 3D from a single measurement. Great. Another problem we have to deal with is that because we're doing single shot measurements, even with the diffuser, there's not much you can do. You have to use those finite number of 2D sensor measurements to get at 4-dimensional function. You're going to end up with a very pixelated 4-dimensional function. And in fact, we design it that way because we want to just barely sample these things well enough so that we can trade resolution for field of view, because getting a large volume is really important to us. And so I don't like the idea of zooming in and getting really good resolution across a really tiny field of view if I don't need that resolution. And we don't, because we're treating these neurons like point sources. I just want to know if the thing is on or not, and know that it's this one and not the one next door. And neurons are big. They're much bigger than the diffraction limited resolution of our setup. And this is where it's like actually a good application for a light field, because the light field always kills your spatial resolution, which is exactly why you use the microscope in the first place. So light field microscopy simply doesn't make any sense to me if you're going to kill the spatial resolution. But here it does make sense because your objects are much bigger than the diffraction limit. And so the idea is that even though it's pixelated, you can still very clearly fit to a line here. And so you can put this sort of like pixelation sampling into your model and still fit this pretty well. And in fact, you can fit the 3D localization of this line. So you can find the slope of this line and its x-intercept with much better precision than sort of the lenslet array size or the pixel size here, which is great because you're kind of doing super localization for things that are off focus. So things in focus, you can only localize to within like the size of the lenslet, but nothing's in focus if you have a lensless system here. So we only want to distinguish and localize. This is quite different than what the previous light field microscopy work has done. But there has already been a couple groups doing really cool stuff using light field imaging for neural activity tracking. So this one's an example. This is a group that does it, but this is not neural activity. But the idea is that it's a single shot 3D measurement, and you can then sort of figure out which neurons are on at which times from it. But we're gonna change our design so that we are opening up a bigger field of view with worse resolution, because we don't care about imaging all the fine details. We just want to see which neuron is on. And we presume that we're using some sort of calcium indicator or something that lights up when it's on, so that when the neuron fires, it lights up. And we just want to say, is it this neuron or that neuron? So we only need about 10 microns resolution in 3D. And we just want to distinguish and localize these different neurons. So we started with some sample experiments. This is just like a bunch of fluorescent point sources in agarose material. So without scattering, so agarose is a little bit scattering even when we call it without scattering, but it's not very scattering. And so what you see is, so the red circles here are where there are point sources that we know because we did 2 photon measurements afterwards. And so you can clearly see some lines here. So this is the raw measurement at the sensor for a light field camera. So this is a lenslet array camera. And then this is the reconstructed epipolar plot. So this is y, theta y, x, theta x along these red slices here. And you can clearly see lines here. So there's not much scattering here. These lines are pretty like thin, but so you can figure out the 3D positions from this, right, as you can imagine. So now we take the exact same setup. So these are static 3-dimensional fluorescent beads, and we simply add 100 microns thick mouse brain tissue on top of it. So this thing is about 300 micron thick sample, and we put 100 micron thick mouse brain tissue on top of it. So the mouse brain tissue is pretty highly scattering. And so the whole thing is 400 microns thick, but only the first 100 microns is highly scattering. And that's actually a really difficult situation to reconstruct. And what you see is like stuff that's near the surface still shows up as these lines. This looks similar to my simulations, but highly pixelated. And stuff that's not near the surface is highly scattered out, right? So this is what your epipolar plots look like, but actually we have the whole 4-dimensional thing. And this looks like a very highly scattered situation that you shouldn't be able to reconstruct, but we actually do pretty well. So if you look, so this is a plot comparing to 2 photons. So we're considering 2 photon to be ground truth. It's a little iffy because, you know, we had to move the thing to the 2 photon microscope. You know, there's some experimental errors here. But the point here is that so light field can compete with 2 photon with no scattering. So these green dots are pretty close to the blue dots. In XY, they're really close. Everything is sort of like on average only like a micron or 2 away from the ground truth 2 photons. So some of these are off, but they could have been like physically moved. In Z, everything is worse. And so in the Z dimension, we have about 12 microns, sort of like how close you can get to it, which is just barely almost good enough, but it should actually be a little bit better. But one of the points here is that with and without scattering, we still do very well at localizing these things. So we're getting through 100 microns thick plus a bunch of propagation. And what I want to show here is, so the red is the 2 photon 3D positions of the particles. And without scattering, I'm showing you the light field reconstruction as I changed. So if I do a light field reconstruction, just shift and add. So I don't use any of our fancy algorithms that account for scattering, then I do this light field reconstruction, and I'm just like increasing the threshold on the light field reconstruction, because that's sort of like what you would do if you wanted to try to find some particles. If you had a light field reconstruction and you want to say where are there particles, you can sort of just threshold it, right? So the blue stuff is all threshold as I increase the threshold from 0 to whatever. And what you see on the without scattering part, it does okay. So if you chose the threshold carefully, you could pick up on most of the particles here, right, in this no scattering case. But in the scattering case, it's just hopeless, that there's no way you would ever actually find these particles from a regular light field reconstruction. And my point is just that the reason we can find them is because of our strong forward model and priors that we're putting in. Okay, so finally getting to the sort of neural activity experiments. Here's our microscope. It's a light field microscope. It's just a regular fluorescence microscope with a microlens array, and then the microlens array is relayed onto the sensor. So the relay is just because we physically can't get the camera up close enough there. And actually now our setup is combined with the 2 photon setup so that we can do our ground truth experiments. So here's the raw data. This is a zebrafish, and so this is zebrafish just naturally behaving, but it's pinned down. And you can see the individual microlenses here. And these two big blobs are the lobes of the zebrafish's brain, the right and left lobes of the zebrafish's brain. So, sorry, there's no scale bar. This is a few millimeters. I think the scale bar is on the next plot. But this is the raw video that we get. And we're just letting this thing have like random, spontaneous neural activity. And we want to decompose it into which neurons are on at once. So we needed an extra step. And basically the extra step is because you can clearly see like stuff is happening. This is the video we have to reconstruct 3D. And stuff is definitely happening, but this is definitely not sparse, right? There's a lot of white space here. And so we needed to deal with the not sparsity because it was killing us. Because if you're not sparse enough, then our algorithms don't work very well. And so the way we deal with it is by doing some time analysis. So we take this video and we do independent component analysis to extract the temporal components. And by temporal components, I mean independent component analysis on the video. So it just takes the raw data as if it was like an X, Y, and then time, and it extracts the temporal components, which mean all of this stuff that is temporally correlated. So each of these temporal components is a 2D raw captured image that represents like neurons that are temporally correlated, that always fire at the same time. And that's definitely going to happen. You're going to have clusters of neurons that fire at the same time. And so these temporal components, the only purpose of doing all of this is to get out a bunch of these temporal components that are more sparse than the original frames themselves. So the temporal components, you can see, have more sparsity in them, and there's lots of them. Then we take each temporal component and say, now this temporal component is sort of a sparse set of neurons in 3D, and now I can run my blob finding algorithm to figure out where those which neurons in 3D are on in this particular temporal component, and then the next one and the next one. So this is a epipolar slice x theta x for a particular slice along, I don't know if it's this temporal component, but one of the temporal components that happens to have 3 neurons on, and we've colored them. So we detected 3 neurons here, and we colored their information pink, yellow, and purple. And now I can fit these to the blob model and figure out exactly where in 3D space each of those 3 neurons are. And so then I basically generate a dictionary. So I take the yellow one and I can generate the like light field measurement that I would have gotten with just this yellow one on. And it includes all of the scattering information because it's really just a decomposition, dictionary decomposition from the raw data. So what I end up with is this dictionary of what we call light field signatures, where each light field signature is the intensity measurement at the sensor that I would have gotten if I just turned on one particular neuron at a time. So I have a different light field signature for each neuron, and for each neuron I have its signature and its 3D position, which I got from fitting the blob model. So this is a calibration step, even though it's done from the data itself. And if we could turn on each neuron one at a time, we would have done that and just gotten these directly, but we couldn't, so we had to do it with this sort of like tricky way with the ICA, but it includes all the scattering and aberrations. That's great because it's just the signature of the raw measurement, not actually a light field, which would definitely have failed. So we built this dictionary. This takes forever computationally, but once we have it, we can just decompose each frame into with a non-negative least squares into this set of different dictionary elements, which represents the set of different neurons that are on it in 3D at that particular time. And that's super fast and efficient. You could do that online in real time if you wanted to. Okay, so then finally, we can do exactly what we wanted to do, which is to track the activity of every neuron over time. And this is a map. This is the 3D map of where the neurons are, and then the color represents their activity at a particular time. And this particular experiment is just this zebrafish hanging around, not really doing much. So it's hard to validate this actually. And you can see some areas, these blue lines are where the zebrafish just like flinched or tried to run away and the dictionary became invalid. We're doing a lot more experiments of like sort of like real neuroscience stuff where we can actually extract like neuroscience results from it. But that's really like in Hilal's lab. And so that's sort of forthcoming stuff. But what my lab is working on is trying to push this thing to the lensless version, which is why I started talking about the DiffuserCam, is that there is no need for this microscope whatsoever because we don't care too much about resolution. That, you know, the size of the neurons is actually pretty big, and so there's really no need for this big fancy microscope here. And so our intention is to replace all of this hardware with a lensless sensor that's just pushed up against the mouse's brain. And we can make a whole bunch of these because they're dirt cheap, and just tile them sideways to get at more volumes. So we're really excited about doing that, but we haven't done it yet. We have this big DARPA project working on that. So I'm gonna end there. My outlook is always the same for all of my talks, that I think computers and optics should talk more, that the synergies between thinking about hardware and software, efficiency from commodity hardware, are really exciting, and there's a lot to be done still without ever having to invent new physics or build fancy custom sensors. So you can sort of prototype these things really quickly. And we do a lot of work trying to make sure everything that we build is easily replicatable. So this is sort of like the open source idea of put the code online, but also make the hardware simple and easy so that somebody can build this thing themselves cheaply and without putting in a lot of time. So we typically also open source our hardware designs. We haven't done this yet for this project, but we will. And so thanks a lot to my collaborators and funding sources, and happy to take questions.
Pretty interesting stuff. We, of course, knew some of it already. Any questions? I guess I have to start again. Laura, you mentioned lensless imaging a couple of times. What, in your opinion, is at the moment the best lensless imaging options of all the options that we have at the moment? Obviously, with lensless imaging, we have always a trade-off between light throughput and depth of field and things like that. You mentioned the DiffuserCam work that you have been working on. There are a couple of other things like coded apertures, like flat cam people use. What, in your opinion, is the best option for lensless imaging for these applications?
Yeah, so I will say the ones I know about are, so we talk a lot with the flat cam people, and what we're doing is different and similar. So one thing that's quite different is, so I think phase masks are fundamentally better than amplitude masks because they're not blocking any of the light, but everybody knows that, right? But there's also a really nice argument for phase masks like this, in that, so if you have an amplitude mask and you come in at it with a point source, you can create this highly structured pattern, which is good, right? Because that helps with the inverse process. But say you have like a extended source in your scene, so it's a bigger object. What happens with an amplitude mask is it's always getting more blurred. So you're always losing spatial frequencies in your measurement. So as your scene becomes not a point source, but an extended scene, your measurement becomes less, it has less and less high frequencies, which is not necessarily true for a phase mask, because a phase mask concentrates the light and focuses it, and focus blurred light out into a point like a lens, right? And this is good because you're actually getting, it helps with signal to noise ratio, and you can have an extended scene that creates a measurement that has the full set of spatial frequencies that it should have. And so that helps a lot. So if you look, all of the amplitude mask people end up with, their images are just sort of like fundamentally always getting blurrier as the object gets more distributed. And that's not necessarily true for phase objects. So I think that's a really great point. There's another trade-off. So flat cam is a lot more like, so Rambus has this lensless sensor that's also fabricated on chip. It's actually much, much smaller, and it's even smaller diffraction elements. So when you go closer to, so our stuff is like several millimeters from the sensor, like 5 millimeters. And that was sort of just because we can't get closer to the sensor without like making a custom sensor, which we didn't want to do. We made these on like 20 different sensors and they all work because it's really easy to get 5 millimeters close to the sensor. So all these other ones are, 100 microns close to the sensor, and that's, you need a custom sensor, you need to fabricate it on, you need very careful alignment. So that's good and bad, because if you get closer, you also want smaller fabricated things, which makes it harder to fabricate, but it means that you can pick up a wider field of view. So when you get smaller features closer to the sensor, you're picking up a wider field of view. Maybe that's what you want, maybe it's not what you want. But that wider field of view also means everything's happening at higher angles. And all of the, so this convolution model that I talked about doesn't work for these other lensless sensors. So of course they're flatter, they're thinner, but I actually don't necessarily think, like we're not pursuing any applications where it's all about being flat. So we will like the neural activity stuff to be flat because it can be compact and attached to the mouse's head, but people are putting like tiny microscopes on top of their head anyways. And the same thing with your cell phone sensor. You can make a lensless cell phone sensor that's thinner, but you know, it's already not that thick, right? Like they've done a lot of work to make these things compact in volume. And what you see with a lot of the lensless sensors, not FlatCam, but actually I think FlatCam does do this, but a lot of them, they do it effectively with their illumination, but a lot of the lensless sensors end up needing an aperture somewhere out here, which is effectively making the volume of the thing bigger. And I think it's very, very hard to create, like I don't think it's gonna replace your cell phone sensor because I think it's very, very difficult to create a like cell phone quality picture without optical elements that fill in a volume that's just as big as the volumes they use now for these cell phone cameras. So I don't think that, I really don't think that's where flat sensors are going. I know that most people doing it also don't think that, but it depends what you want to do. So I think for us, the DiffuserCam is cool because it's so simple and easy. Like you're literally taping these things on. You can try it. You can build this thing in an hour and calibrate it and get it working within an hour. And you just tape it on so you can pull it off so you're not wasting a sensor if you screw it up. So for development purposes, it's really cool. As far as like the inverse model, I think there's a lot of issues around calibration, right? So most, so the Rambus people, and then there's some folks in oh, I forgot which company, like Hitachi, I think, doing this that are using like just Fourier transforms. So they're all doing 2D imaging where you say it's in the far field, and far field happens sooner if everything's smaller. So if you get closer to the sensor, you can call it far field sooner. So in the far field, you're not getting any depth information. You can't do 3D stuff, but you also can use this beautiful like convolution model where it's just simply FFTs. So you get really fast computation on the reconstruction. That is really useful. The sort of like, if you want to do 3D, you have to come closer, and then all of these, you're not in far field, so the convolution model breaks down. And so then what people have been doing, and also for the bigger ones, if you have multiple scattering in your like if you have a thick mask use, then you can't just use this convolution model. And so you have to like basically brute force calibrate, we call it, where like you basically turn on a point source and move it all through your scene and take a calibration measurement, but then you end up with this massive calibration measurement, and people haven't dealt with that well yet. They just make their images small, like they solve for like 100 by 100 pixels or something like that. And their calibration process ends up taking like forever. And so it's very, very impractical, but I think it's more accurate. So our convolution model will break down if we use diffusers that are stronger and put them closer to the sensor to get this bigger field of view. And so we've been playing around with trying to, like, you know, it's this trade-off between the physical model is really useful for the inverse problem computation-wise and for calibration, but it might be less accurate. And so we've been playing around a lot with sort of hybrid models for like physical modeling plus sort of like not brute force, but taking it in a few positions and sort of correcting the problems you get with the simple physical models. So I think it's really just all trade-offs. But like for what we're doing, I think that the DiffuserCam kind of makes sense. And so that's what we're pursuing, but it's also not really that different than a lot of these other approaches.
But I think calibration is one of the keywords. Depending on the application for making this replicable, I think using a diffuser would require an individual calibration because every diffuser has its own point function. If I have a coded aperture with the same pattern, then I can assume that ignoring calibration on the sensor, I maybe avoid calibration for different.
Yeah, so not true, because the diffusers are these Newport diffusers. They're actually holographically defined, and every single one is exactly the same. but you would never want to not calibrate. So like everybody calibrates, everybody who designs their own mask calibrates it, because there's no way of placing it exactly. I mean, maybe if you were trying to mass produce and you had a factory doing this, you could do it. But for research grade stuff, everybody's calibrating because there's no way of getting these things exact. So another calibration important thing is like your Z position, right? So this is something that we've definitely seen. If you try to build a light field, you can do a light field like microlens, lensless sensor, and you need to get that microlens placed. Okay, so in XY, you can figure it out if it sort of like doesn't exactly match the pixel pitches. You know, even Litro calibrates, even though Litro has everything like carefully defined and they still calibrate every single sensor. But the Z position is really important. It has to be exact. Whereas with a diffuser, it doesn't have to be exact. And our calibration is just a single point source in the far field, so it's really easy. So you take one single image and your point source in the far field doesn't really have to be in a particular position. It's just that everything will be referenced to that. So I would actually argue that I don't think that anybody's doing this without one image calibration. And by your argument, we could actually do no calibration as well, because we could pre-measure these diffusers and they're all the same. Just use the same part of this diffuser for each one. But I mean, we're never going to do that. We're always going to calibrate because it's not possible to place things exactly, I think.
What's the resolution requirements on the sensor side to resolve the point spread function of the diffuser?
Yeah, so this is really important, and actually a lot of the flat cams I've seen get this wrong. So what you want is to have, so say you have a point source in the far field, then you measure this point spread function. Then depending on the features on the mask and how far it propagates, your point spread function is going to have a certain set of spatial frequencies. And you want to Nyquist sample those spatial frequencies, right? So if you oversample those spatial frequencies, then when you do this, like, basically your scene is the Fourier space intensity. And so when you do this convolution model, you're just doing a deconvolution, but everything is sort of like, if you oversample, then everything is stuck within a small bandwidth within your big Fourier transform. And this is obvious, right? Like you've just wastefully oversampled the thing. But you see this in a lot of lensless imaging cases where they kind of like get this wrong because they designed to Nyquist sample a single point source, and then they put in these extended scenes that really like kill their bandwidth of their measurement. And so you end up with reconstructing like really tiny pictures within a big space. And that's really just about design. And so something that's actually really nice. So you can, when you're designing your masks, you don't have to think about this. You can design them carefully for this, I mean. But for the DiffuserCam, we're just using off-the-shelf diffusers, but you get to choose, like there's like, you buy a kit with like the half-degree diffuser, 1 degree diffuser, 5 degree, 10 degree, and that's about like how much angle spread they have. So like 10 degree diffuser is stronger than 5 degree. And we actually do choose those pretty carefully such that when they're placed at their caustic distance, the spatial frequencies that they create on the sensor will be Nyquist samples by the sensor. So we've built this on the Raspberry Pi camera. We built this on sensors with 1.3 micron pixels, 5 micron pixels, and 10 micron pixels. And you just change which diffuser you use and what distance you place it at to match the pixel sensing, which also changes your field of view range of angles. But you know, we haven't cared about that. So you just end up placing your object in different positions depending on what you want to do for that. But we do think about that. The sensor choice is actually usually our sensor choice is more importantly decided by, so cheap, because we wanted to do it on Raspberry Pi. But some of our stuff was on like fancy SCMOS cameras. But one of the most important sensor metrics is its angle sensitivity, because that's essentially usually what limits your actual range of angles you can capture, which limits your optical resolution, is the range of angles to which the sensor is sensitive, because these sensors are designed to go in photography cameras or microscopes where the NA is extreme, or the F number is extremely high or the NA is extremely low, which means that most of the light is coming in on axis. And so they're not designed to work very well for light coming in far off axis. And there's a significant fall off of their sensitivity when the light comes in at high angles. And actually that is the limiting factor for most of these sensors is like, that's what defines what's your effective numerical aperture, which defines your optical resolution limit, is the angle sensitivity. And if you use backside illuminated sensors, they always just have sort of like more uniform angle sensitivity, because they don't have a bunch of circuitry on top of the sensor, which causes all kinds of weird changing angle sensitivity with position of the pixel, which can create major problems. So if you brute force calibrate, you don't have to worry about that, because it'll calibrate out, although it will be the limiting factor. But for us, because we're using a model-based system, if we don't use backside illuminated, then we would want to also like put in that like angle sensitivity curve into our model.
So let's assume a sensor that's 50 centimeter in diameters and pixels are in the millimeter range. Would that work with your diffuser?
I think you would use a different diffuser. You would use a like more weak diffuser. So you'd use a diffuser that has like smaller bumps, and you would place it further away, which would mean that your range of angles would be smaller, but that could actually be really good, because if your range of angles is smaller, then the breakdown of this convolution model simply won't happen, because the convolution model is completely valid, you know, plus minus 15 degrees in either direction. And once you go beyond that, it starts to sort of gracefully break down. And so we fight that a lot, where if we could have bigger pixels, bigger sensor, we would get better baseline, so we would get better depth resolution, and we would have, it would just be easier to deal with, because it would satisfy the model better. So actually we would love to do that. And we've talked about going to giant sensors. We just haven't done it yet.
We have a couple of giant sensors here, but the problem
oh, cool.
that these sensors are basically a plastic film. So they are bendable, they're very large, and we are at the moment at optical imaging options in a lensless fashion, because the whole camera system that we want to build should be, including the sensor and the optical imaging part, not bigger than 1 millimeter, but it should be scalable up to several meters.
Oh, so that's cool.
We have been looking at coded apertures, for example. At the moment, we did some work with collimators, with solar collimators, but of course, the problem with all of these approaches is that they are not very efficient in terms of light throughput.
Yeah, so you could presumably buy, like the privacy glass sticker can work, right? So we sometimes use the Newport diffusers, sometimes like just on Amazon buy this privacy glass sticker, which is totally flexible as well. So you could potentially use that, but I think it would be too diffusive for really large pixels. But I know like Ashok, that was his original intention with the flat cam, was to build like sort of like flexible sensors. So I know he's thought about that quite a lot. Could be really fun. We had played around. So my students did a class project where they used a scanner there's like scanner cam. So we have like sheets of this diffuser that are like 2 feet big. So they tried like putting that in front of a scanner, but the scanner still has relatively small pixels because it's scanning. So, but it was a humongous image.
Okay, any more questions from your side? Anna? Anybody else? Okay, thank you very much, Laura. Again, very, very interesting talk. Thank you.
Okay, great. Thanks. Okay, bye.
Bye-bye. The next talk will be by Markus Steinberger of TU Graz on the 21st of June, and he will be talking about visualization. Yeah? GPU schedule. Okay.